Hello everyone and welcome to CRAMSURG, Clinical Research Appraisal and Methodology for Surgical Trainees, where we pick a paper fresh from the press on a hot general surgical topic. We review it for you, we present it for you, we critique its methodology for you, and provide top-of-the-field expert opinion and teaching on research appraisal and methodology. My name is Gio Perrin, and together with Professor Sababala Subramanian and Maria Digby, we bring you CRAMSURG from the wonderful region of the Yorkshire and the Humber. Tonight we're going to carry on our statistical tests and how to guide set of presentations. We're going to talk about two-way and Welch's ANOVA. So the usual set of disclaimers. I'm not a statistician, so I'm not an expert in stat software, but I kind of like both a little bit. So over the years, I developed some experience. A brief summary of what we talked about last time. We talked about assumptions. We now talked about assumptions for 3 talks, and we're going to talk about it today again because assumptions are important. So I just want to make sure that you remember them. We talked about students T. We talked about ANOVA and how to do them, which I hope you remember. If you don't, go back to our website and there's our lovely presentations. Just to carry on our plan and our path, we're still talking about continuous data. We're still talking about normally distributed data, and we are still talking about this particular column here, about comparing more than 2 groups together. And we are talking today about variation types of ANOVA. And we're going to do our demonstration with Jamovi, which is what we've been doing all the way through. So compared to last time, we're going to try and answer a slightly different question. So last time we were wondering what tests can we do when we have collected numerical data from a number of different crops, a number of different groups of patients, etc., etc. And how do we know if that data that we collected from different groups of patients is actually different? Today we're going to try and determine if there's 2 factors that can affect 1 factor in different groups. And we're going to give you some practical example to explain that a little bit better. And then if you remember, we said that ANOVA can be used only if the data is homoscedastic. That is to say the variances of the groups that you've got are comparable. Today we're going to see what we can do if the data is not homoscedastic. So let's try and explain a little bit better what we do if we have 2 factors that we're interested in. But we're going to do a two-way ANOVA. We're going to talk about it. And if the data is not homoscedastic, we're going to do a Welch's ANOVA. And again, we're going to talk about it a bit more. We talked about Fisher last time, and we talked about how he was working on crop statistics. And all the things that Fisher is famous for. Now, the two-way ANOVA came out about 3 years after the description of the original ANOVA. So it took him a little bit longer to come up with this. But it was kind of revolutionary at the time. Because it was really, really hard for people working in the agricultural industry particularly, but also in a number of other professions, to try and work out if they were doing the right thing when they were starting a process, and if the results that they were getting were influenced by different actions that they were performing throughout, for example, the cycle of growing barley. So if ANOVA was useful because it would let you compare 3 crops of barley, when you put 3 different types of fertilizers, perhaps Fisher wanted to know, well, what happens if I put a bit more seeds down when I'm planting the barley, as well as using different fertilizers? Is there a way of knowing if putting more seeds and putting a different type of fertilizers work better than putting less seed and putting a 3rd type of fertilizer, and so on? Is there a way to know if different planting concentrations and different types of fertilizer interact with each other in a positive or a negative way? And those were all questions that at the time were very, very difficult to answer. Fisher worked really hard on this and came up with his two-way ANOVA. To recap how ANOVA works, ANOVA looks at variances between the different groups that you're analyzing and within the groups that you're analyzing. So we talked last time about between group variation and within group variation. I'm not going to go into too much details, but I just want you to remember that because it's kind of important. And as we said last time, the basic principle that drives ANOVA is that for a certain amount of within group variability, you expect a certain amount of between group variability. If there's too much of one or the other, you think that the populations are different. So there is a statistically significant difference. Okay. The assumptions that we are considering for a two-way ANOVA are very similar to the assumptions that we are considering when we're looking at a one-way ANOVA or a standard Fisher ANOVA. The first assumption to check for is always normality. Always normality. I don't think I've said that enough, but it's very, very important. And the second one is obviously skedasticity, as we said. So we need to make sure that the samples that we are comparing have comparable variances as well. And again, we went into some details on this last time, so I'm not going to be too tedious. And these other assumptions also remain true. So samples have to be random, the samples have to be big enough, and there has to be independence in the samples and variables that you are looking at. For example, the two variables that you're trying to test, in this case, we talked about the planting concentration and the fertilizers, they have to be independent from each other, not related to each other. For example, if you use different types of fertilizer and then you look at the concentration of nitrogen in the soil, those two are going to be somehow related because the fertilizer puts nitrogen in the soil. This might be a bit of simplistic explanation for people that do planting on a regular basis, but that's sort of how I understand it, at least. So we will demonstrate the two-way ANOVA at the end of the talk. Now, let's see what we can do when actually the data is not homoscedastic, but is heteroscedastic. And that's where Welch's ANOVA comes in. Now, Welch is somewhat less famous compared to Fisher. Now, we looked at the Wikipedia column of things Fisher is famous for. For Welch, that's pretty much a little square. However, Welch was actually a very important figure in statistics in the 1950s. This is a picture of him. It's an extract from a picture from the 70s when he was working in Leeds. He was head of statistics department there. He published numerous times. He was associate editor of the Journal of Royal Statistical Society. And he did attend UCL, where he was influenced strongly by Fisher himself. Welch was born in Sunderland, so he was a northerner. And again, he spent the vast majority of his professional life in the north in Leeds. But he studied in London. He was a big fan of Newcastle, what I hear. Right, so we said that Welch's ANOVA allows us to determine whether there's a difference in two populations or more populations, even when the variances of those populations are different. Nevertheless, we still should remember that the other assumptions that are valid for a standard ANOVA still stand here. So your data still has to be normal, the samples still have to be random, still need to be big enough, and the samples need to be independent from each other. So, a quick recap of what I mumbled so far. Two-way ANOVA, we are going to look at how two factors, going back to our example, planting densities and different fertilizers, affect one, which is obviously the yield of the crop, and how they interfere with each other. And Welch's ANOVA is what we use when we want to know how one factor affects a particular outcome, and we have multiple groups, such as different fertilizers in different crops, and we want to know if they affect the yields and how much. But we use it when the data is heteroscedastic, but still normally distributed, as I said numerous times. So to give you a practical example, we're going to go back to my lovely dissertation data set, and we're going to try and do two things today. If you remember, my dissertation was about collecting data about papers that were advertised on Twitter by 6 different publishing journals and look at the retweets that those tweets were getting. So question one we're going to ask ourselves is there a difference between papers published by different journals or published as open access or not in terms of retweets? So how belonging to a particular journal as a paper or being published as open access or not can affect the number of retweets. Again, assuming that our data is normally distributed and homoscedastic. Question number two is there a difference between papers advertised at different times of the day in terms of retweets? And we're going to do that using Welch-Sanova because the data is going to be heteroscedastic. Well, we know from our previous examples that the data is going to be heteroscedastic anyway. But we're still going to use it as if it wasn't, if that makes sense. So let's bring in our data set. Again, Jamovi makes this very easy for us. There's a big flag up here that says ANOVA. So we are going to start with two-way ANOVA. So not one way, but simply ANOVA. It's labeled as such. I'm not entirely sure why, but that's where you find it. Our dependent variable is going to be retweets. And we said we were going to look at the different types of journals publishing and open access status, which is this one. And as you can see, Jamovi spits us out a very nice output, which tells us that the journal titles, so the journal that's publishing and advertising, does affect the number of retweets in a statistically significant way. And there's 5 degrees of freedoms because there's 6 journals. Open access status is not statistically significantly associated with the number of retweets. And it also tells us that the interaction between the two is not statistically significant. We can also run some assumption checks, which will, as we expect, tell me that I shouldn't have run this test, but I've done it anyway, just to show you how to do it. So we will run a normality test, because normality is very important, which, as we discussed numerous times now, is the Shapiro-Wilk test. And as you can see, because there is statistically significant result here, we know that our data is not normally distributed. So we shouldn't have run this test, as I said before, but we've done it anyway, just to show you how to do it. And if we run a homogeneity of variance test or Raven's test, again, the variances are not equal between the groups. So again, we should not really be running this test, but nevertheless, we've seen how it works. Now, very quickly, let's forget about this for a minute and do a Welch-Sanova. So Welch-Sanova on Jamovi is found under one-way ANOVA. And actually, Jamovi automatically acts as if the variances are not equal. So it runs this as a Welch-Sanova as a baseline. And we said we were going to look at retweets as our dependent variable. And we were going to look at different times of the day. Because, you know, surgeons are up at 4 a.m., so they want to know if their tweets are going to be retweeted equally at 4 a.m. versus midday. And as you can see, different times of the days, according to this particular test, do statistically significantly affect the number of retweets that you're going to get. So be careful what you do with your X. And again, we can run some assumption checks, which are very well displayed here on Jamovi, homogeneity and normality. I've just explained them, so I'm not going to explain them again. And again, this tells you that, well, it's fair game that there is difference in variances. That's fine when we're running a Welch ANOVA. That's the whole purpose of Welch ANOVA. But it is not fine that the data is not normally distributed. So again, I shouldn't have run this test, but I have done it in order to show you how to do it. That's it for today. Not entirely sure what we're going to talk about next time. I have a few things in mind. But yeah, let me know if you have any questions or if you found that this was a bit too complicated.